Okay, so chapter 12 has to do with kinetics, which is the study of the rate of reactions. So we know chemical reactions require varying lengths of time for completion. For example, we know if you light a match, it burns immediately. Some things you mix together and they come together quite quickly, a precipitate is formed or something like that. But other reactions may take a lot longer. For example, if you have some iron furniture outside, it may take years before you notice rust starting to occur. So a lot of times they can do various speeds. So the reaction rate, how fast the reaction goes, will depend on a lot of things, the characteristics of the reactants and the products, and mostly the conditions under which the reaction is run. So as we learn about this, what we're going to do is eventually apply it to what's happening at the molecular level. All right, so what are some of the things we're going to talk about in this chapter? How is the rate of a reaction measured? What conditions affect the rate of the reaction? How do you express the relationship of the different variables with respect to the rate? And what is happening on a molecular level during a chemical reaction? All right, so like I said, chemical kinetics is the study of reaction rates, how reaction rates change under different conditions. So in other words, how fast does a reaction go? What are some things that affect a reaction rate? And you may know some of the things right off the top of your head. You may take a minute and think about it before we move on. A lot of times temperature, you can make a reaction rate go faster if you heat it up. If you put things in contact with each other, making it easier for them to be attracted to each other. Surface area, you know, if you react to things that aren't in touch with each other, the better you get them in touch, so forth. So let's go through these. So concentration is important. The more molecules you have to react, often the faster they react. Use of a catalyst, that's something I didn't mention earlier, but yes, a lot of times we use a catalyst, something that speeds up their reaction, but the catalyst itself isn't used up. The temperature, probably the first thing that comes to mind when you think of speeding up a reaction. And like I said, the nature of the reaction. So are they solids, liquids, and gases? Are they in the same phase? Are they in touch with each other? Going back up to concentration, you know, think about it. If you light a match in the open atmosphere, it's got a percentage of oxygen that burns it, you know, and the rate will go moderately fast. But what would happen if you light a match near 100% oxygen atmosphere? Like if you had an oxygen tank and it was open or something like that, if you had much more concentrated oxygen, it would go faster. So these are some of the variables that we're going to look at, things that affect the reaction rate. All right, so like I said, let's look at each one individually. Concentration of reactions. More often than not, the rate of the reaction will increase when you increase the concentration. And now we haven't talked about it yet, and we will by the end of this chapter, but in order for a reaction to happen, the molecules have to be in contact with each other. They have to be close to each other, because otherwise they can't react. So it makes sense that the more molecules that you have around, the more likely they're going to interact with each other and the faster the reaction. So sometimes we will say that a reaction happens by a collision. The two molecules have to hit each other. So again, increasing the population of reactants increases the likelihood of a collision. Now, I do want you to take note that it says more often than not. It doesn't mean always. So there are times when increasing the concentration does not affect the rate, and we'll talk about that at some point before the chapter's over. Like I just said, in some reactions, the rate is unaffected by the concentration. As long it has to be present, but it doesn't. The concentration won't affect it. Like I said, we'll talk about that at some point. All right, use of a catalyst. Probably you may have thought of this when you think of speeding up a reaction. A catalyst, like I said earlier, is a substance that increases the rate of a reaction without being consumed. In other words, it may get used in the reaction, but then it's regenerated. So you end up with your catalyst at the end. So it's not a reactant because it's not consumed. Catalyst doesn't generally appear in the overall equation because it's not used, although sometimes we indicate that it's around by putting the formula over the arrow. This is an example. H2O2 will decompose to H2O and O2, and here in this case HBr is a catalyst. Other catalysts that you may be aware of are metals, like in your catalytic converter in your car. Those are the metal often makes a reaction go faster. Okay, the concentration or the use of a catalyst is important. So this is the equation we just looked at. Usually what it does is it speeds up a reaction by reducing the activation energy. We'll talk more about activation energy in a little while, but you can imagine it's the amount of energy that you need to get the reaction going. So if you need a lot of energy, what you can do is you can use a catalyst which will lower that energy in some way, making it easier for the reaction to occur. Sometimes, like I was talking about metals, sometimes catalysts just provide an alternate mechanism, a different way of going, or a different pathway, or the metals often attract the molecules closer to each other, making it easier for them to react with each other. And so there's lots of different ways that catalysts might affect the rate of reaction. But they always, basically what they're doing is lowering the activation energy, lowering the amount of energy needed in a number of ways. Okay, temperature. Temperature is, like I said, a really probably a common one that people would think of. Generally speaking, if you're trying to make a reaction go faster, you heat it up. So usually reactions speed up when temperature increases. And why is that? You may remember from when we talked about the gas laws. If you increase the temperature, what's happening? Molecules are moving faster. Well, if they're moving faster, they're more likely going to collide with each other, or more often, more likely, and collide with more energy, which gives them more energy, enough energy to get over the activation energy. So it increases energy. So just a good rule of thumb is that a reaction rate approximately doubles with a 10-degree rise in temperature. All right, and then like I said, nature of reactants is important. For example, if you're reacting a solid and something else, the surface area must be considered. So, the more places that the two reactants touch, the more likely the reaction will go faster. If you've got a thin wire as opposed to like a thick piece of metal, it may make a difference. Also, charged particles are attracted to each other more than non-charged particles, and so oftentimes you see things like, that's why precipitation reactions happen so fast. Those ions are attracted to each other, and so they generally happen very quickly. So, and like I said, if two liquids aren't soluble in each other, so again, if they're not in the same phase, the surface area or the places where they touch becomes important. It's just different types of reactants, the activity of them. So an example here is that as you move down the group alkali metals, the faster they react. And so it could have to do with how easy the electrons, in that case, electrons are being removed from the metal. So it's much easier to remove them if they're farther apart. But anyway, just the nature of the reactants can affect the rate of the reaction. All right, so let's talk about what is a reaction rate, and hopefully you understand the idea of a rate. Another example, would be your your driving speed. So, we don't say, oh, when you say you're going 60, you're not saying you're going 60 miles. You're saying you're going 60 miles per hour. So, you have to have both the amount and the time that it happens with in order to have a rate. So you're going, 60 miles in 1 hour, whereas if you're going 60 miles in a day, you'd probably, probably if you were crawling. Anyway, so the reaction rate is an increase in the amount of a product formed per unit time. And of course, it doesn't have to be hours. It could be minutes. It could be seconds. It could be years, but per unit time. So usually we look at how much of the product is increasing over time, or we can also express it as how much of one of the reactants is decreasing over time. And since it's chemistry, probably the most likely unit that we'll be looking at will be the molar concentration, so molarity. Just going forward, if you see a compound written inside brackets like this, with the brackets, what that means is that this is in the concentration of molarity. So whatever compound you're talking about. So we often will use these brackets as an indication that we're talking molarity. And I think you can use other concentrations, but for this course and for this chapter, we'll talk about molarity. Okay, so let's consider this reaction. 2 dinitrogen pentoxide decomposed to give us 4 NO2s and 1 O2. So one thing we can do is we can pick one of the products, it doesn't matter which, but we'll say, okay, how can we measure the change in the concentration of O2? So the way that we're going to write that is we're going to denote molar concentration using our brackets, like we said, and then when we have a change, we use, of course, the term delta. Delta just means change in. So delta O2 just means the change in concentration of molar concentration of oxygen. So again, that's what that symbol means, the change in the molar concentration of O2. Or another way, let's erase that so you can see what that says. Another way to see that is to take the final concentration of O2 minus the initial concentration. That's always what delta means, final minus initial. All right, so then, how much, that's not very useful without the time. So over a given time interval, we have delta t. So again, delta t is the final time minus the initial time. So the molar concentration of O2 will increase by delta O2 over delta t, and that would be the rate of the reaction then. So rate of formation of oxygen will be delta O, change in concentration of O2 in terms of molarity per change in time. And like I said, the time could be hours, seconds, minutes, whatever you're measuring it in. And so this equation gives us the average rate over the time interval t, delta t. Here just shows another way. So the rate of formation of oxygen, delta O2 over delta T, is the concentration of O2 at a final time minus the concentration of O2 at the initial time, divided by the difference between the final time and the initial time. So if you allow delta T to get shorter, smaller and smaller and smaller, and some of you may recognize that as integral or differential calculus, if you get that smaller and smaller, you get what's the instantaneous rate, so the rate at any particular instant. What's the difference if you think about, your average rate? Let's say you drove, you went 60 miles in 1 hour. Well, it doesn't mean that every single second of that hour you were going exactly 60 miles per hour. You may be maybe were going 85 at one point, and then you saw a policeman and you slowed down, and maybe you were going 55, or maybe you were going 45 because there was a traffic jam or whatever. But your average, if you went 60 miles in an hour, your average rate would be 60 miles per hour. How, compare that to what are you driving right at this instant. At this instant, you might be going 75 miles per hour or whatever. So that's the difference between, as you get smaller and smaller time interval, at this certain instant, you can get your exact instantaneous rate. So if you look at a graph like this, this is showing the increase in concentration of O2 over time. And so you can see here at time 0, there was no O2 present because we hadn't made any yet. And then they're measuring it in time, 1200 seconds, 2400, so forth and so on. And you can see that what this looks like, you can see that the line is increasing. But notice that it kind of starts to level off here. Well, so if we wanted to find any delta, any change in concentration, any rate of reaction, we could pick any 2 units of time and any 2 units of concentration, which we'll do on the next slide, and find the average over that amount of time. And as it said on the previous slide, if you want to know the instantaneous rate, what you're doing, like let's say we want to know right at that instant in time, what is the rate? What you can do is take the tangent of the line, the slope of the tangent of the line at that point, and that will give you the instantaneous. But you can find any average rate by taking any change in concentration divided by change in temperature, time. So I believe I have some on the next slide. Maybe the next slide. So one thing that we noticed is we saw the increase in concentration of O2 during the decomposition of N2O5. Note that the rate decreases as the rate proceeds. So let me draw it up here again. So it kind of not very good, but you get the idea. It starts out, let's try that again. It starts out kind of slow or fast, and then eventually the rate slows down. You can see that it levels off. Why is that? Well, imagine the rate, if you react to anything, the rate goes fast at first, but as those molecules react and get used up, you've got fewer of them the concentration drops, you have fewer of them to react, and so the rate will slow down. And you've probably noticed that when you do a reaction, eventually it does slow down or even stop. So again, as more reactant gets used up, the fewer molecules there are available to react, and so naturally the slower it goes, because we just said that concentration often affects the rate of the reaction. So here's what I was saying. If I want to, let's look at this interval right here. If I want to know what's the average rate of oxygen increasing over this interval, and so I can find the change in concentration. And I just read the dots, and it's coming from this data here. You can see that these points were plotted, and so this is 0.2 and 0.3. So at 600 seconds and at 1200 seconds, and so the delta concentration, change in concentration, is 0.0036 minus 0.0021, which is 0.0015. And the change in time is 600 seconds because it's 1200 minus 600, so 600 seconds. So the rate over this interval of time is 0.0015 moles per liter per second. You could say moles per liter per second, or you could say molarity per second. So if you divide that out, you get 2.5 times 10 to the minus 6 molarity per second. That's the change in oxygen over that time. Notice that we did the same thing at this interval. So these would be points, looks like 4800 and 4200. So the difference here in concentration goes from 0.0075 to 0072, which is 0.0003. And then again, it's another 600. And you don't have to pick 600. It just happens to be these are the two that we picked. You could do it at any two intervals. You could even do, you know, this point and this point and get an average rate for the whole reaction, or from start to finish, or whatever. But we just happen to pick certain intervals to do this. So the increase in oxygen concentration here is 0.0003 molar over 600 seconds is 5 times 10 to the minus 7th. So you can see that clearly the rate has decreased over time. It's gotten a bit slower. All right, so I just showed you, this is what I just did on the last slide. So if you take the 2 points, and delta O2 divided by delta T gives you, this is the first set of conditions, and then over time at the second set, there's my equation, and you can see that the rate has definitely slowed down. All right, now we don't have to only look at products being formed, and if you noticed in that last example, there were 2 products being formed, so we picked the oxygen, but you don't always have to. You can define the rate of reaction in terms of any of the reactants or products, and they're all related to each other because the equation's related by stoichiometry. So we can express the rate of any of them, but notice that we want to express the rate. Now that, what we were talking about, delta concentration of whatever divided by delta T is the rate of that one. But if you're wanting to compare them to each other, then you have to look at stoichiometry. So for example, this would be the rate of decomposition of N2O5. Notice that this one has a rate, we make this, the rate is negative, and this is just by just normal, this is the way we represent it, is that if something is decreasing, we make it negative because it's going down, and so a negative of a negative will give us a positive. So the rate should always be, there's no such thing as a negative rate. The rate should be always positive, but we put the negative there to say, okay, overall the concentration is decreasing, so the rate will be positive if we have a negative, and then this change will be negative as well. So the negative and the negative will result in a positive rate, and that's what we want, because rate should always be positive, but because it's something that's decreasing, we use the negative. And then we can compare them within our balanced equation. So notice that 1 O2 is formed, but at the same time 4 NO2 are formed and 2 N2O5 are formed. So are removed, and so are react. So let's compare what we can compare the rates of each one of them by dividing by the coefficient. So let's think about this. So we need 2 N2O5s to decrease to get 1 O2. So that means the rate of O2 increasing is half as fast as that of the N2O5 decreasing, because there's 2 of these decreasing for every one of these increase. So it's the rate of N2O5 decreasing is half as fast as the O2 increasing. So notice all I did was just divide by the coefficient. And I put the negative because it's decreasing. In a generic formula, then we could say that everything's related by stoichiometry. So if you just divide by the coefficient, so the change in A over time divided by little a will equal, and notice that's negative because A is decreasing, is equal to negative rate of 1 over B change in B over change in T, or 1 over C change in C over change in T. This one's positive because it's increasing, and 1 over D delta D over delta T. So as an example, if I want to compare what is the rate of I3 compared to I negative, well, the change in concentration of I3 over time is equal to negative 1/3 the rate of I negative, because this will decrease 3 times faster than I3 increases. So if we divide by 3, we'll make them equal. And because this is decreasing, it becomes negative, and because this is increasing, it is positive. So the rate, these two rates will be equal to each other if I divide this one by 3.